Hello everybody, welcome back to Unit 6. Today is Lesson 2, and we're talking about inverse trigonometry, angles of elevation and depression, and basically problem solving with trig. The idea here is you are expanding your trigonometry horizons and make it more versatile and useful for you. And you wanted to be able to, very simply today, describe how to find missing angles of right triangles if you are given only the sides. The idea here is that you're going to learn one basic skill, but then we're going to just really expand on it and go crazy in depth with it. So last class you learned about 3 trig ratios to find missing sides. Okay, but what if we need to find the missing angle measure of a triangle? Well, that is when we use what's called inverse trigonometry. We basically work backwards to find an angle by using 3 sides of a right triangle. So we've given this angle, or this triangle ABC here, and we want to know the size of angle A. And I've gone ahead and written out all of the trig ratios. This is a quick review for you guys. You've already done this in the last class, but what a lot of students will start to say is, I need to divide both sides by sine, and would say, that is wrong. You cannot divide by sine, because the trig ratios are actually trig operations. So we want you to figure out something else. Well, how do we work backwards from operations? We perform inverse operations. So the way that we write the inverse of sine is not by dividing and not by subtracting. It's sine to the -1 power. Okay, but we don't read it as sine to the -1. We say sine inverse. And whatever we do to one side, you have to also do to the other side. So if we're going to take sine inverse of sine of A, then what we see is the inverse and the thing itself are going to cancel out, leaving us with just angle A. That's exactly what we want. On the left-hand side, we have sine inverse of 3/5. Pull up a calculator and we can find this very simply. First thing you need to do is divide that 3 divided by 5. If you're using a scientific calculator like your phone, you do that part first. Now, for just about every other phone calculator, you can get to those second features or the trig features by tilting your cell phone to the landscape orientation. For any other scientific calculator, find your trig options or press the second button and you should be able to find your trig options. So we go into trig and I choose second, and there we can see sine inverse. Sine inverse of 3/5 is 36.869, or to 3 sig figs, that will be 36.9 degrees is angle A. Now, we can do the same thing just to verify for ourselves. It doesn't matter which trig ratio you use. You just have to use the ones based on the sides that you're given. So if I were to take the cosine inverse of both sides here, we should get the exact same results. Cosine inverse and cosine will cancel each other out. And when I take 4 divided by 5, and I take the inverse cosine of that, I get exactly the same thing, 36.9 degrees. And then you can probably guess what's going to happen next when we take tan inverse of both sides here. Those are going to cancel out. And just to prove it, we can say that 3 divided by 4. Then we take the inverse tangent of 3 divided by 4, and we do indeed get the exact same result, 36.9 degrees. All of those are the same for angle A. Whichever inverse trig ratio you use, you will get the same result. So what you just need to remember and apply to every one of these other problems is that remembering that trig ratios are really just operations, and you don't divide by trig, you don't subtract by trig, you perform inverse trig operations to isolate angles. Now, for these next few problems, I would like for you to apply what you've learned, choose the right trig ratio based on the sides you have for the reference angle that you need to find. Okay, so usually the most challenging part of a problem with trig is drawing the picture that's going to accurately reflect the situation. So let's take a look at an example together. I want to solve the triangle, which means find all the missing sides and angles in triangle ABC, where angle C is a right angle, B is 15, and C is 20. And I want to write down the things that I know and that I don't know. So I don't know side A, that's one thing that's going to be missing. I also don't know angle B, and I don't know angle A. So it might seem like we don't have enough information to go off of, but since we know it's a right triangle, we actually do. So go ahead and draw a right triangle. And it doesn't matter exactly what the proportions are of your right triangle. That is not important. What's important is at least that you label the correct right angle, and then you label the sides based off of that. So side C is going to be the one opposite of that. That's their hypotenuse, and that's going to be 20. Now, I could go ahead and use angle A or B in either one of these positions. It does not matter. I'm just going to go ahead and arbitrarily call them A and B, and then you have to just set the sides accordingly. So angle B is going to be, or side B is going to be the one down here that's opposite of that. Now, it could end up being that side A is actually longer than side B. I don't know which one is going to be which here, but that doesn't matter. You have to kind of get out of your head about that and just trust the trig process. Okay? Now, pick an angle arbitrarily to decide which one you want to solve first, A or B. I'm going to go ahead and choose angle A just because I usually like to start at the left and work my way over. That's just the way that I am. So, angle A is going to be over here, and I recognize that I have an adjacent side in 15 and a hypotenuse in 20. An adjacent and hypotenuse is going to allow me to utilize cosine to find angle A. So cosine of angle A is going to equal 15 over 20, which then tells me that I can use inverse cosine to isolate angle A. Go over to my calculator and plug this in. And the inverse cosine is 41.4 degrees, rounded to 3 sig figs, but I'm going to leave it a little bit further than that, just in case there's any intermediate rounding that I need to worry about. Don't round your answers until the very end, just in case you're going to be using those values later. You want as many digits as possible. So angle A is going to be 41.4096, so on and so forth, degrees. Now, once I have that, I can find angle B really easily by using the triangle sum theorem. And we can say that angle B is going to equal 180 degrees minus the right angle, 90, minus 41.4096, so on and so forth. And that's going to give us a good approximation for angle B. So let's go ahead and do that. We have 180 minus 90 minus 41.4096, so on and so forth. And that gives us approximately 48.5904. So angle B, 48.5904, so on and so forth. And now I've got my two I've got my two angles. And now what we can do is let's go ahead and round them to our 3 sig figs at this point for our angles, and we'll call that 48.6 degrees. And angle B, or angle A, is 41.4 degrees. Sorry for mixing and matching my notation here. That's just the way that I roll. I like to be confusing. Sorry. Now, our last thing that we're missing here is side A. And again, we could use Pythagorean theorem to find that side, but let's use trig. Trig's more interesting. Let's try it and find that. I like trig rather than doing the Pythagorean theorem. Anyway, so side A. Side A is my opposite side, right? And so I can use either tangent or I can use sine. I always liked to use sine. That's just the way that I am again. So I will say that sine of angle A is going to be my opposite side, side A, over my hypotenuse of 20. But now that I know what angle A is, 41.4096. Again, this is where you want to make sure you don't use that intermediate rounding. Don't use 41.4. That's not as precise as we could be. So you go ahead and use this 41.4096 degrees. And that's equal to A over 20. But I know that I'm just going to end up multiplying 20 on both sides. So I can just say this, multiply by 20 here. Those will cancel out. And I'm left with 20 times the sine of 41.4096 is going to give me my side A. And we now have side A is about 13.2 rounded to 3 sig figs. And there you have it. We have solved the triangle. So on the next page, you guys have a triangle that you can sketch and solve on your own. Good luck with that. Come back when you're ready to talk about angles of elevation and depression. All right, angles of elevation and depression. Well, finding heights and distances of very tall or far away objects has been a common problem for humans for thousands of years. And you guessed it, trigonometry helps. So what you want to think about is, I want to start thinking about triangles in everyday life. When I look up at something and I consider an imaginary straight line going out from my eyeballs, I'm forming angles. Okay, an angle of elevation is when you're looking at something and you're looking up at an object. That angle formed is the angle of elevation when you're looking upward. If you're, however, looking downward at something, that's going to be an angle of depression. But even things at ground level can have angles of elevation to look up on top of things too. So we love, as geometry teachers, to ask all kinds of questions like this. Hey, how tall is that tree over there without having any other kind of measurements? Or how tall is the flagpole that's sitting on top of this building? Okay, and the way that we are able to do that is by these angles of elevation and depression. And these were always able to be found by these really old devices called inclinometers. And inclinometers are just these like little plumb bomb attached to a telescope that can show you what that angle actually is of the thing that you're looking at. So super cool tool, super helpful, and provided great use for nautical adventures throughout the millennia. Now, let's go ahead and consider a classic example. Somebody is standing on top of a cliff. So a person is 1.5 meters tall and stands atop a cliff that is known to rise 20 meters above sea level. The person sees a boat out at sea at an angle of depression of 8 degrees. So I always like to try and recreate my scenario. Go ahead and channel your inner artist here. And that's okay. All right, now I've got my person that's standing on top of the cliff, and they are looking out straight as a horizontal. That's going to form one part of your angle. The other part is what's going to go down at the boat. And the angle that we are looking at is going to be 8 degrees right there. So you can do this a couple of different ways. You can look at the triangle that's formed right here, going up to the person from the sea, out to the boat, and then from the boat up to that person. And if we know that angle of depression is 8 degrees, then I also know that this must be 92 degrees because I've formed myself a right angle. Not 92 degrees, excuse me, that should be 82 degrees. Now, I also know that the height here is 20 meters for the cliff, plus the person is 1.5 meters. So that's a total of 21.5 meters from here down to here, adding in the person of the height. Now, of course, we're assuming that their eyeballs are directly on top of their head, but it's such a small difference, we're just going to kind of roll with that and just be okay with it. Now, from here, we want to find this missing side here. Okay, so we can use angles of elevation and depression because we're given that angle. We know one of the sides. We know that this is going to be forming a right triangle. Then we can use trigonometry to work with this. So this side here is going to be my adjacent side, and this side here is going to be my opposite side. And which one we'll use, opposite and adjacent? That's going to be tangent. So tangent of the opposite side, the thing we want to find over 21.5. Oops, excuse me, I need to have my angle in there. Tangent of my angle, 82 degrees, is equal to opposite over 21.5. Now, we'll go and multiply both sides by 21.5. Those will cancel each other out on the right-hand side, and we are left with a simple calculator process here, where we will take the tangent of 82 degrees, and then multiply that with 21.5. And we'll get our result of 152.98. Since we don't have to work with anything else here, we don't have to worry about the intermittent rounding. So we can just say that distance to the boat, the opposite side, is going to be approximately to 3 sig figs, 153 meters away. So you have now an example, another classic one. Tell me how tall the tree is by knowing the distance of its shadow and the angle of elevation. Go ahead and try that one on your own. All right, our final task is really putting everything together here using right triangles to try and deconstruct shapes. So right triangles can be found in squares, rectangles, non-right triangles, hexagons, pentagons. They are everywhere. If you look for them, you will find them, and you can use trig to solve some really, really cool problems. So let's take a look at this really complicated one without giving very much information, but we can find something very interesting. Now, A new feature at a botanical garden will be a regular pentagonal flower bed with sides length of 20 meters. We want to find the width of land D required for the flower bed. So I'm giving you a hint here. The triangles meet at the center of a regular pentagon are equilateral triangles. Oh, that's not true. I apologize. These are not equilateral triangles. Okay, we don't know that they're equilateral triangles. However, I do know that this distance and this distance and this distance and this distance and this distance, since this is a regular pentagon, these are all congruent to each other. Now, they may not be 20 meters. I don't know if they're 20 meters, to be honest. I don't think they are, but I don't know. So I'm going to try and figure out what can I do. Well, if all of those are the same distance, then it's like a circle. And that's my radius. And that's really important to think about this as a circle, because that's going to tell us one thing. All of the degrees in a circle, from starting at one point going all the way around, are going to add up to 360 degrees, which means any one of these angles can be found by doing 360 divided by 5, which is just 72 degrees. So now that I know that this is going to be 72 degrees, that's going to be really, really helpful. Every one of those interior angles is going to be 72 degrees. Why? Why is that helpful? Well, let's go ahead, clean up a little bit of mess, and let's focus on one of these triangles. Knowing that that angle is 72 degrees, I want to deconstruct this into a right triangle. If we look at that, now we have a right triangle. If I draw a perpendicular bisector, and since I know that's a perpendicular bisector, that means I know that this length right here is half of 20 meters. That's 10 meters. And I know this right here is going to be half of 72. That's going to be 36 degrees. Okay. Again, I know that because this angle right here is going to be 72 degrees. So what do we need to do now? We need to find this length first, and then we are going to need to find the length on top of that. It may look or seem like those are going to be identical, but they are not quite. Not quite. So let's go ahead and first find this one in blue here, since I can use trig to find that one very easily. Okay, I have my opposite side over here, and this one is not the hypotenuse, this is the adjacent side. So I can take the tangent of that 36 degrees. Will equal the opposite 10 over that adjacent side. And that's that distance to the center from the bottom of the pentagon. Okay, so rearranging this, we can say that the adjacent will equal 10 over tangent of 36 degrees. And we'll go to our calculator to plug that in. And that will give us about 13.7638. Again, we don't want to round that yet, 13.7638. So on and so forth. Okay, now let's go ahead and try and find this missing side here. How do we find that? Well, that is congruent to our hypotenuse. Look at that. We don't even have to change triangles. We can go with the same triangle. Right? So that means I could use cosine of 36 degrees because I know what my adjacent side now is and the hypotenuse, or I could use sine and use this 10 meters. So let's use that because that's a little bit cleaner. Let's go ahead and use sine of that 36 degrees will equal that 10 meters, that's opposite, divided by our hypotenuse here. And now we just want to rearrange. Again, I'll multiply both sides by the hypotenuse, and then I'll divide by the sine of 36, and the hypotenuse will equal 10 divided by sine of 36 degrees. And we get 17.0130. Now, we can go ahead and add those two values together. D will equal 13.7638 dot, 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 plus 17.0130, dot, dot, dot. And if we add those two together, we should end up with 30.7768, dot, 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 or approximately 30.8 meters. And that is our distance. Just with a little bit of trig, not very much information, we can solve all kinds of interesting problems. This is where the creativity comes in and the fun of geometry and trigonometry comes in. Find those right triangles, you can find them everywhere. In fact, you can even find them on the roof of your house. Go ahead and try this UDO example. Come into class ready with questions. Thanks for watching. I will see you next time.